In this video, we are going to talk about rational inequalities. Just like polynomial inequalities, if f of x is a rational expression, then we can have one of the four scenarios. F of x is less than 0, less than or equal to 0, greater than 0, or greater than or equal to 0. Let's try to understand this concept in a graphical sense. The graph of y is equal to f of x is given. Solve the inequality. F of x is less than 0, and that means we're referring to y is being negative. So we're looking for anything that is below the x-axis. So that would be this section and this whole curve, all below the x-axis. Now let's determine the x intervals for those pieces of the graph. With the first curve, I see that x travel from negative infinity all the way to negative 2. So the interval would be negative infinity to negative 2. And then the second curve looks like it goes from that vertical line, so that's from positive 2 all the way to the right. So that's going to be 2 to infinity. Part B, f of x is less than or equal to 0. This time, not only we will include the interval, but also the points, any points on those pieces of the graph that land on the x-axis, because those are the x-intercepts that has y is equal to 0. And I see only one point, so that's going to be from negative infinity to negative 2, so we do include that negative 2. But the second curve, as you can see, it never crosses the x-axis, so that's going to stay the same as 2 to infinity. Next, we have f of x is greater than 0. That would be anything that is above the x-axis, and I only see this piece. And in that piece, let's see where x travel. It goes from, looks like negative 2 all the way to 2. So we're going to write negative 2 to 2 and don't include those values. Especially don't include 2 because you can see there's a vertical asymptote there where the graph will never cross that vertical asymptote. So it will never cross this line here. So x can never be equal to 2. Part D, f of x is greater than or equal to 0. So again, anything that lands on the x-axis. So that's going to be this point again. So with that interval, we'll modify it to be bracket negative 2 and 2 parentheses. So negative 2 is included, but 2 is still not going to be included. Now let's try a problem without a graph. And I'm using the same 4 steps as before. First, express the inequality with one side set to 0. So it looks like we are going to need to move 3 over to the left, so minus 3 is less than or equal to 0. That's not enough. We need to combine these as one single rational expression. So I am going to make 3 over 1. Because they have different denominators, one is x minus 2 and the other one is 1, we do need to find the least common denominator, which in this case, it is just x minus 2. So we are going to multiply both the numerator and denominator of the second term by x minus 2 so that the two denominators will be exactly the same. So keep the first expression the same. The second expression, properly distribute the negative 3. So we should have, and we can merge that as one expression now because they have the same denominator. So it distribute negative 3, we get negative 3x plus 6. And then that's less than or equal to 0. In the numerator, you can combine like terms. So 4x minus 3x, that's x. And then negative 5 plus 6, that's 1 plus 1. And at the end, we end up with this expression here. Step 2, find the real solutions of the related equation f of x is equal to 0 and any values that make f of x undefined. So we're going to look into f of x is equal to 0 first. So that's x plus 1 over x minus 2 is equal to 0. A fraction is equal to 0 if and only if the numerator is 0. So x plus 1 must be 0. Therefore, x is equal to negative 1. Now we need to look into when f of x is undefined. Because this is a rational expression. A rational expression is undefined when the denominator is 0. So x minus 2 equals 0 means x is equal to 2. We are going to use these values in step 3 as boundary points. So create a table. I'm going to put the lesser value on the left and then the greater value on the right. Negative infinity, positive infinity. In fact, let's move these points up above the line. Now draw the columns. And I want to make a little note here. The f of negative 1, so when x is negative 1, f is 0. So f of negative 1 is equal to 0. And when x is 2, the function is undefined. So I'm going to put f of x is undefined here, where x is equal to 2. Now let's test points. So we have negative infinity to negative 1. Any values in between, just pick something easy to plug in. So let's pick negative 2. And then between negative 1 to 2, we can pick 0. And then between 2 to infinity, let's say we pick 3. Now let's substitute them in. And I'm going to use this simplified expression here to substitute these values. So x plus 1, we're looking at negative 2 plus 1 over negative 2 minus 2. So negative 2 plus 1 is negative 1 over negative 2 minus 2 is negative 4. So a negative divided by a negative should give us a positive. Next, 0 plus 1 over 0 minus 2. That's positive 1 over negative 2. That will result in a negative. X is equal to 3. 3 plus 1 over 3 minus 2. That's a positive 4 over positive 1. So that will result in a positive as well. Back to the original problem. We want the form where the function is being compared to 0. So this is where the function is, we want the function to be less than 0. So that means it's negative. And also equal 0, less than or equal to 0. So we also pick the value negative 1. So when you write the interval, it's going to be negative 1 included to 2. We cannot include 2 because 2 is where it makes the function undefined. So the final answer is negative 1 to 2. Let's try this next example. X squared over x squared plus 4 is greater than or equal to 0. Step 1, we want to make sure the other side is 0, and it already is. So put a check mark there. Step 2 is where you find the boundary point. So look into two scenarios where the function is equal to 0 and where the function is undefined. So equal to 0, that means numerator has to be 0. Therefore, x is equal to 0. The function is undefined when the denominator equals 0. So x squared plus 4 equals 0. You subtract 4 from both sides. You get x squared is equal to negative 4. And then you take the square root of both sides, but we can't take the square root of a negative number. So this one actually has no solution. So what it means is x squared plus 4 can never be 0. So therefore, the function is never undefined. So I'm going to put the answer as none here. There's no x values that will make the function undefined. So the only boundary point we have is the point 0. So we're going to test the values here. Create a table. We put 0, and then negative infinity, positive infinity. Pick a value that's less than 0. Let's say we have negative 1. And pick a value that's greater than 0. Let's say 1. And we're going to plug it in. So we have negative 1 squared, in parentheses, over negative 1 squared plus 4. So that's 1 over 1 plus 4 is 5. So it looks like it's positive. Of course, we make a little note here that f of 0 is equal to 0. And then x is equal to 1. So 1 squared over 1 squared plus 4. That's 1 over 5. So it's also positive. So in the end, what is the final answer? What values makes the function positive or 0? Positive means you accept all of these. And when is the function 0? That's when x is 0. So it looks like we accept everything with no exception. So the final answer should be negative infinity to positive infinity. And finally, this problem. So this problem looks exactly like number 5, but instead of greater than 0, we have less than 0. Now, looking at the table, we could use the same table that we created here. And I don't see anywhere where f of x is less than 0. So that doesn't exist. However, it is possible for x squared over x squared plus 4 to be equal to 0. And that is when x is equal to 0. So the only solution that we should get here is x is equal to 0.